Good morning, calculus. Let's see here. Symmetry is what we're doing today. Let's see. Goodbye, you. Share a screen. All right, we got this. Get rid of that. Cool. How's everyone today? Got any room in your brain for some more knowledge? Anything you want to ask about before we look at the glories of 5.4? Let's see, how shall we kick this off? So 5.4, title of it in the book is Working with Integrals, and really it's just kind of a bit of a chance to kind of soak for a few minutes on, I don't know, shortcuts a little bit, maybe a little bit of the applications before we sort of wade into what I alluded to before, which is just trying to take the integral of everything. Because as I mentioned, and this is kind of what we're going to tackle really in the next section, 5.5 would be something more like this. If I said, what's the integral of x times the cosine of x? You're not going to get rid of that. Like, that's a multiplication that can't be multiplied out, unlike your assignment yesterday. So you got junk times junk there. And so from Calc 1, you think, that was product rule. That was fairly complicated to take the derivative. And now I actually got to go backwards somehow. And so you're not going to make that go away and turn into a bunch of plus signs and just be the power rule that we looked at yesterday. And so, that's where this class is going. Today is really kind of a pause in the action in that regard. The other one might be something like, and so this one's going to take a technique that we'll learn later called integration by parts. You don't need to know that now. But what about something like this? What if it wasn't just, say, the sine of x, but what if it was the sine of like x, say x squared? Again, you say, hey, junk inside of junk, that was the chain rule. Taking the derivative going forwards was the chain rule. That was kind of complicated. The derivative of sine of junk is cosine of junk times the derivative of the junk. So somehow we got to do that in reverse. And so, we got to come up with some way to tackle that. Again, you're not making that go away. In the last section, it looked like it was going to be confusing, but then because you're able to do algebra, then it just became the power rule. But you're not going to get rid of the fact that this is junk inside of junk. You're not going to get rid of that. And so tomorrow, what is today? Thursday, Monday then. Monday, we'll look at a technique called substitution that's actually going to allow us to answer that kind of question. So that's the, I don't know, the overall, the rest of kind of where this class is going is just tackling random questions like that and seeing if we can find the area under those curves. But today we're really just going to play around with something that might save you a little bit of time here and there. It's just kind of something interesting to think about, and then a couple of applications. So let's see. I know this is 5.5 for sure. I'm not sure where integration by parts is. Since I wrote it down, I think I'm going to tell you really quick. No, it's not for a long time. Wow, it's actually not clear until chapter 8. We're going to learn substitution, and then we're going to be able to apply it. So there's going to be all of chapter 6 will be applying it to something kind of neat. So this isn't clear till chapter 8, which is crazy, I think. Anywho, 5.4. Start off with something simple. I think I can spell symmetry. Is it 2 M's? I'm not sure. There are some graphs that are symmetrical that will save you a little bit of time. So this is a bit of just a little side trail. Like it might save you a little bit of time. You should be able to look at that and say, hey, that's a parabola. And the 1/2 will make it a little wider than a normal parabola. And then the 4 is just going to slide it up 4. So I would say then the graph of this thing would probably look something like this. If I just draw a rough graph, you shouldn't need a graphing calculator to tackle this. So, maybe it looks something like that. And so if I do this, then if I said, as we've been doing, what's the integral from say 1 to 4? Fine. But what if I said from 3 to -3? Why is that kind of going to save you some time? Or what do you suppose is going to happen there? Maybe I'll make that a little bit better since I am giving the hint that this has to do with symmetry. What do you think's true about that area?
You could do 3. Is my mic working? Can you hear me?
Yep, sure can.
Okay. You can do 3 to 0 and then times it by 2 because it's equal on both sides.
Yeah, that's exactly right. And that's going to be important for the applications we get to in a little while. And I don't know if that saves a lot of time, but remember, anytime one of those limits of integration is 0, you're really happy, because when you're plugging 0 in, you get 0. So it saves a bunch of time. So the fact that the area on the left of this is exactly the same as the area on the right of this means I could say this is equal to from 3 to 0 of 1/2 x squared plus 4. And again, I was lazy and kind of forgetting that little dx on the end. Except I'd have to multiply by 2. Double it. Okay, that's not that complicated to see. That makes all kinds of sense, I think. So again, you should be relatively good at the power rule. Again, I say that in quotes. Add 1 to the exponent, divide. So that'd be x cubed. If I divide by 3, then there's already a 2 down there, so that'd be a 6. And notice the cool thing about integration is the 4 was a constant, and yet it sort of grows an x, if you will. So the integral of 4 is 4x. And so then when I go to plug 0 in, there isn't going to be a 4 there. Like every term has got an x in it. Therefore, when I put 0 in, it's going to be 0. So, and sometimes this is another, and notice the 2 is gone. So occasionally you'll see kind of this written almost like a box like that, so that you have a place to put the 2 out in front, because I do need to multiply this whole thing by 2. So, okay, fine. That's probably worth knowing. That'll save me 10 seconds. So 3 to the third is 27 divided by 6 plus 12. I get 16.5. So that'd be 33. So we sort of got lucky. And again, I hope it isn't lost on you that we just found out the area under that curve, and this drove the ancients crazy. Keep in mind, if this was centimeters, that's 33 square centimeters. Exactly 33 square centimeters, meaning if you had 1 centimeter by 1 centimeter, that's what a square centimeter is, that it would take exactly 33 of those to fill that space, even though it's curved. And so they described that as squaring the parabola. In other words, they made squares out of it. And it's just crazy that that would be exact. You'd think it would never have an exact answer when it's curved. But apparently, in this particular case, it did. What if you had done this the long way? Just to kind of reinforce this idea here a little bit. What if you had done this the long way so that you still had x to the third over 6 plus 4x, but you evaluated it 3 and negative 3? I mean, the answer is still going to be 33, right? But how's that going to come about? Like, what are you actually going to see happen when you do that? What is this going to look like? Well, we already plugged 3 in and we got 16.5, and we know it's always minus. What's going to happen when you put negative 3 in?
Get negative 16.5.
Yeah, notice that number is cubed, so negatives are going to stay negative. And then the 4x is x to the first, so you're going to get two negative numbers and you're going to get negative 16.5. I mean, that's the other way to think about this is, hey, it's a waste of time. I just had to plug it in twice. And as you know, sometimes if you plug a negative into your calculator and square it, like you'll actually get the wrong answer. So you can see perhaps that's a time savings, I guess. But again, I find this a little bit weird because you have to actually know something is symmetrical. But what other kind of graphs are symmetrical besides parabolas? Can you think of any?
Trig functions.
Yeah, no trouble, Alicia. Like a trig function, like cosine.
Wouldn't like cubed equations be symmetrical, but like in the wrong way? Like, wouldn't you get kind of like a 0?
Yeah, good question. So let's just write a couple of those down because I'm not going to belabor this point very much, but like cosine looks like this, doesn't it? So it's perfectly symmetrical on the y-axis. Now sine has a symmetry to it, but it's not symmetrical on the y-axis. So if you had a problem, well, I think we might have had one like this yesterday, actually. Now that I suddenly think about it, it was something like cosine of x plus 1 or minus 1 or something. And the values, we evaluated it from pi over 2 to negative pi over 2. So same thing. If this was evaluated from the same number on the right as it was on the left, so from k to negative k, do you understand the logic of that? That's the kind of thing you might see in a textbook. Like pick any number you want, as long as one of them is positive and the exact same number is negative. And again, you can mess with cosine a little bit and it stays symmetrical. Like I can add 7 to it, which just pushes it up, which is what I did to the parabola a minute ago. Or I could multiply by cosine by something which just makes it steeper. So the things you can do to mess with it and it remains symmetrical. But that's of course going to be equal to 2 from k to 0. So that's going to save some time. What about what I think it was Connor that said this? What about the symmetry of something cubed? It has sort of a form of symmetry too. And by the way, I don't actually know the answer to his question right now, but do you know what x cubed looks like? I'll exaggerate it a little bit over here, but x cubed kind of looks something like that. He's right in the sense that, well, in one sense, let's draw a picture of it. So if I said from here to here, isn't, because of the symmetry here, aren't those two areas going to be the same? He's right. But what am I going to get for an answer if I went from, say, 5 to negative 5 on this graph?
You would get a 0, right?
That's exactly right. Since one of them is below the graph instead of above it, you're actually going to get 0. So they are the same. It's just one will be positive and one will be negative. So that's kind of interesting. So that's kind of a different sort of symmetry. Again, what I'm really interested in here is not some memorized technique to get these problems done quickly. I'm just more interested that you notice that sometimes you do get areas that are identical to each other. So that's kind of interesting. So he is actually onto something. So that's just kind of cool to think about. What about something like this, though? And I want you to just do this since you know how to do this. If I give you x squared plus 4, but then I said minus 2x, do you agree the minus 2x just screwed that parabola up in the sense that it's not symmetrical on the y-axis anymore? So you're not going to multiply this by 2 and kind of get the answer, right? And we'll graph it maybe in just a second and note that. So I'll say not symmetrical about the y-axis. But if you were evaluating it from, say, 3 to -3, notice that's symmetrical. 3 to -3, in other words, it's the same number twice. I just want you to solve this in the way that you know how to solve it and see if there's any, I don't know, time savings. So the graph isn't symmetrical, but the limits of integration are symmetrical. And again, I forgot the dx. Check to make sure you didn't get the integral wrong. Are you getting better at the power rule in reverse? Are you getting faster at that? It's kind of unfortunate. We're getting a lot of the same numbers here. I guess I'll leave it. So the question is there any time savings in the fact that both numbers were 3? I mean, since we're raising them to powers. So when I put -3 in and cube it, because it's cubed, it's actually going to stay negative. So it becomes -9. But -3 squared is +9. And so -3 times 4 is -12. So you get, of course, you get the same numbers, right? Same exact list of numbers. That's what you're going to get. But the signs are a little wonky, right? In reality, because it's squared, does it make sense those two terms are going to cancel? Because this squared cleanses the number of its negative sign. So it being squared, it doesn't care that it's a positive or a -3. So notice you end up with -9 minus a -9. You end up with -9 plus 9. I probably should have made it up an example without this being a negative sign so that you can see that happening. But that middle term would cancel out there every time. Now the odd exponents of x to the third and x to the 1 aren't going to cancel out. But do you notice in the end you end up with, because of these two, you end up with 9 plus 9. And because of these two, you end up with 12 plus 12. In other words, really, you ended up kind of doubling the first number and doubling the third number. Now, again, in my opinion, this is an utter waste of time. And like, I'd have to concentrate too hard to notice, hey, here's a situation where I could save 20 seconds. I'm probably safer just to say, I'm just going to work it out. And so it takes me 10 extra seconds. So I think this is worth stopping to consider, but I want you to understand on a test, I'm not even going to ask questions like use symmetry to, save 10 seconds and get this problem right. But it is just interesting to notice. And there, when we get into some of the applications for this, that'll make a bit of a difference later on. So you end up sort of, I guess I'll say it this way. You end up with 2 times 9 plus 2 times 12, because the 3's are going to produce the same exact number in both problems. And because you end up subtracting a negative, you end up doubling it again. So you can't just double the answer like you doubled it before. But interestingly, you still are kind of doubling some of the answers. And so that's just interesting. If I was writing this textbook, I don't think I would even included this. I don't know. Is this worth considering? I don't know. Not really sure. 18 and 24, what is that, 42? Feels like I should at least write the answer down. Again, crazy, but the area under that parabola was exactly 42. I don't know if there's any profit in this, but let's just take a second and graph that. So we've got x squared minus 2x minus 2x plus 4. I'm going to hit zoom 6 so that I get a standard graph. Hopefully I can see the whole thing. So if I cheat and actually ask it for the answer from -3 to 3, hopefully it agrees with my 42. So again, it's crazy that that comes out exact, but, and we aren't going to go down this road, but is there a place, is there any other way to think about symmetry here? Is there any, I mean, I still have symmetry in this picture. I guess I would have symmetry from, and you should be able to figure out that low point right there. Maybe quickly from last term, how would you do that? Well, that's where the slope would be 0. The slope of x squared minus 2x plus 4, the slope of that is 2x minus 2. 2x minus 2 is 0 at 1, x is 1. And so x is 1 is the low point. So it would be symmetrical from 3 to 1, which is a distance of 2, and then from 1 to -1. So even though the axis isn't in the middle of this graph, it's still, I mean, I could sort of move the axis over here and make it symmetrical in that regard. And so, I don't know if that's worth thinking about, but it's just interesting. So whatever, there's a couple of questions in your assignment about symmetry. Let's move on to something a little bit more practical now. Stop sharing that screen and go back. So we're going to look at a simple application now. And this will likely be something you've never really thought about or considered before. But if I ask you what the average temperature yesterday was, for instance? Why is that actually a really complicated question?
Because throughout the whole day, the temperature changes.
Yeah, it's kind of changing constantly. Now, it would be easy if you did it this way, and this is what you've always done to find the average of something. If I said at hour 1, the temperature, I'm just making this up, the temperature was say 32 degrees, and at hour 2 it was 35 degrees, and so forth, and I had 24 temperatures there, then you would say, oh, the average is easy. I add up 24 temperatures and I divide by 24 and I have the average temperature. The point is, you're used to adding up a finite number of things, a limited number of them. But how many temperatures were there yesterday? To Caesar's point, there was a lot of temperatures because the temperature actually changed, well, continuously. The temperature is actually different a billionth of a second later. I mean, you can't measure that with the tools that we have, but it's actually changing constantly. Right now, it's working its way up. When I left the house this morning, it was like 34, and it's working its way from 34, and it's hitting every number of all the decimals on its way to 35. And so, does it make sense? What you're being asked to do there is, well, what am I being asked to do? Well, now I'm not going to have 24 temperatures. I'm going to have billions of them. Well, you can add up a billion temperatures as long as you divide by a billion, right? So how am I supposed to do this? If I really wanted the right answer to the average of something that changed continuously, how am I supposed to figure that out? Well, let's do something to make this a little bit realistic. Let's say, so hour 1, I'm thinking, right after midnight. I'm just going to making that up. Let's go into, I don't know, the morning, like 10 o'clock or something like that. And say it made it up to 40. And then it got probably the warmest, maybe around 1 or 2, which would be hour 13 or 14. And then it kind of started going back down again. So let's take it to, I don't know, 7 o'clock, which would be hour 19, and say it kind of went back down again. So we'll say now it's down to like 35 or something like that. So let's just say we took a sample of those temperatures, but we understand logically that they're going up and going back down again. And so that happens kind of on a daily basis, but just for the fun of it, and because I want you to learn to speak the language of math, not just calculus, I'm going to take those 3 numbers and I want to find an equation that models them. And actually, let me ask you that. What equation would model this? What kind of an equation models something that goes up and comes back down again? What options do I have?
A cosine.
You could, sorry,
Keep going. Cosine, I'll write that down.
you could do a negative parabola.
Yep, the parabola. And I like that you pointed out that it was negative, because to be upside down, it would have to be negative to be facing down. Yeah, that's the 2 that occurred to me. And it doesn't have to be a cosine wave. It could be a sine wave because they're the same exact thing. Cosine would do a better job of modeling day to day because it's the same exact sequence the next day, but with a slight modification. Maybe overall there's a trend toward warmness or whatever. So I don't know, we'll think about this. Well, one of the things I hope you can do, because of your knowledge of algebra in general, because this is one of the things you actually could get paid to be able to do, is model things like this. And so I hope you are good at regression. Let's see. Actually, I think I'll show you this in the graph. I think I'll show you this in Desmos. Have I ever showed you how to do regression in Desmos before? Those of you that I had before. Desmos is such a better machine anyway. Why don't I show you? Why don't I teach you that at the same time? hope I remember how to do it now that I made that promise. And so part of me wants to pick the parabola because we're really good at taking integrals of parabolas. But cosine feels more realistic, but I don't know, let's play with both of them. Let's see, so I have the Desmos app on here and let's play with this. So what you got to do in Desmos is you got to enter the data in just like you do in your calculator. Let me see, is that the plus sign there? Yes, it is. If I hit the plus sign and I put a table in, well, now I'm going to put in my numbers. Oh no, they're gone now. I don't remember what they were. Hour 1, it was 34. Hour 10, it was 40. Tell me if I got this wrong. And hour 19, it went back down to, I forgot, 35? Is that what I said?
The first one was 32, not 34.
This one was 35, is that right? So one of the cool things about Desmos is it sort of knows you want to graph these automatically. Like you have a place to enter data and the graph happens automatically. So how do I get it to make a cosine wave? Well, in your graphing calculator, you have to go to a different button. But here, this is kind of cool. Notice those points are not labeled X and Y. They're labeled X1 and Y1 because this is one table and I might go on to make a second one. If I made a second table, it'd be X2 and Y2. So I can go right here. And the amazing thing about Desmos is you can make up any equation you want. You don't have to stick with a simple list. You can make your own equation up for this. So a parabola would be something like, well, I say Y, but I can't say Y. I got to say Y1 because it's referencing that table up there. So I say Y and I just hit 1. And it automatically knows that's Y sub 1. It didn't say Y times 1 when I did that. So I'm really thankful for that. And then you normally say equals. But this is new for Desmos. I can't remember how I figured this out. You got to go hunting, and I don't remember where this is. So hopefully I can find it without too much trouble. There it is. I think it's tilde, T-I-L-D-E, right there below the B and the N. Is that right? Tilde, T-I-L-D-E. That's sticking in my head for some reason. It's kind of like one part of an approximately equal to. I think that's why they're using it here. And I'm saying this is a parabola. So the downside of Desmos is you actually got to make the equation up for yourself. You got to know what parabolas look like. So parabolas look like ax squared plus bx plus c. So ax squared plus b, and then I can pick any letters I want. I'm just picking the ones that we classically pick. Bx plus c. What did I do wrong? I did it on purpose, but what did I do wrong here?
You need to make it negative.
Don't have to make it negative. Now you could do that yourself, I think.
You have to put the 1 by the A's, right?
Yeah, you got to get the 1 in there. Remember how it wasn't Y, it was Y1? Well, it's the same for X. It's not X, it's X1. So I got to go back there and put that 1 in. So I purposely left it off just to highlight it to you because when I was first learning this, I was constantly doing it wrong. Notice it says, oh, okay, great. Are you surprised that that's perfect? Do you notice it says that right below the equation, statistically R squared equals 1? That's kind of that's saying it's 100% accurate. Notice it perfectly goes through there. If you know your algebra, you're not surprised this is perfect. And I'd be impressed if you did know that actually. Again, Math 261 in the spring is studying linear algebra, which is this process. But does it make sense? I have 3 points here. And so if I was to plug in the first equation, if I put in 32 for Y and 1 for X, I would have 32 equals A plus B plus C. That's an equation with 3 unknowns. Well, I have 3 points. So I'm going to have 3 equations, 3 unknowns. There is one answer to 3 equations, 3 unknowns. Now, if I'd muddied the waters here, I'm going to erase this, but if I had muddied the waters back in this, why can't I get out of there? By going back to this, let's see, enter, is that what I do? And I said at hour 13, the temperature made it up to say 42. Does it make sense it's now not perfect anymore? And notice my answer there was a little unrealistic, like based on the data, it's like that couldn't have happened. Obviously, you just made that up because that didn't work. Maybe 41 would have made it a little bit better, or maybe even 40. But do you see the R squared value is 0.9994? It's like 99.9% accurate, but it's still not perfect. So that's what would happen in the real world. Like you'd maybe list 6 or 7 temperatures and it would say, well, there's a parabola that approximately models this. But just for the sake of keeping it simple for us, we're just going to make it really easy and let there be just 3 temperatures.
Doug, would this have worked for our chair project last term?
Yep.
Wish I'd have known this.
Would have been nice to know, huh?
This is using a matrice, right?
Yeah, that's right. This is using matrix algebra, which is what you formally study in Math 261, linear algebra. And notice our equations are linear. Well, you might think, no, it isn't. It's a squared equation. But as soon as you plug in x is 1, you get a times 1 squared plus b times 1 plus c, a plus b plus c. The a's aren't squared, the b's aren't squared. The things you're hunting for are just numbers. So a is not the sine of a, it's not a cubed. So that's linear algebra, 3 equations, 3 unknowns. It can be done by hand, but it's awesome when you don't have to. Notice, however, that A, B, and C aren't really very nice. And so what I'd like to know here is the average temperature for the day, which is from hour 0 to hour 24. Because that's, you can appreciate that's kind of an interesting question to ask. But the problem is you have a billion temperatures, right? That's not good. So how am I going to add them all up? I mean, I have an equation now, so I can plug in hour 1, hour 1.1, hour 1.2, hour 1.3, and I can get all the temperatures. And if I did what I just said, 1.1, 1.2, 1.3, that would mean 10 times as many temperatures. So instead of 24, I'd have 240 temperatures. Does it make sense? It would be a Riemann sum estimate if you added all 240 of those temperatures together and then divided by 240. That would work. Or what if I went every 1/100th? So I start at hour 0, hour 0.1, hour 0.2, hour 0.3. Now I have 2,400 temperatures. And then I divide by 2,400. Those would be great estimates, wouldn't they? But really time consuming. Take a guess at this, like what you think the answer to this is. Like, I just want you to guess the average temperature, and notice it's from 0 to 24. And I'm gonna help your brain here right now. Watch what I do. This is kind of cool. But if I say y equals a, notice I said a, x squared plus, I think this is gonna work. I actually don't know. I may be over promising and under delivering here. Plus c. Oh, it did work. And I'm going to go back and turn the blue graph off, like don't graph the blue graph, I'm saying. Since I now have values for A, B, and C. Now, the only reason I did this, because that looks like a waste of time, is now I can go back in here and limit by saying I want X to be greater than 0 and less than 24. You're getting some free Desmos knowledge here. How do I get the right side of that guy? Second, that's how I do it. Then I could even turn those points off now. Does it make sense? That's the whole day now. So I couldn't have limited the domain. I really was only looking from 0 to 24, but I don't know about you, but it's hard for me to stare at a graph that goes forever and limit my thinking to 0 to 24. But what would you say is the average temperature there? And I wish we were in class, because I'd make you write it down and I'd throw a Snickers bar to whoever gets lucky enough to get this right. But of course, you're just guessing someplace in the center here. Now what I'm going to do is take a screenshot of this so that I can draw on it. Get it back into our notes.
Hey Doug,
Yep, go ahead.
is it does Desmos not let you put limit your domain in the other equation?
No, I don't. Actually, I'm not sure. I was thinking it probably wouldn't, which is why I took the trouble to rewrite it. But I have a feeling if you went in there and tried to add something after that, it wouldn't let you do it. But I actually could be wrong.
I'm curious as to what would happen. I mean, I would try it, but you can move on if you want.
While you're thinking, if I have you do something, I probably will go back and try that. I'm glad you asked. I'm sort of curious too, now that you say that. Okay. So I don't know, I'm guessing, doesn't the average look to be maybe about here? I'm gonna make my guess. I'm gonna say right just below that line. Let's see what's that worth, 32, 34. I'm gonna guess the average. If you're taking statistics, that's a symbol for average. X bar is also a symbol for average. I'm gonna guess 33.6. That's my guess. So you make your guess. Now, what do you do? And this is what I've been showing you and why I spent a little bit of time conceptually on, what integrals are. Does it make sense you're adding infinitely many things now? Like this is what integrals do really well, is add infinitely many things. We can't add infinitely many. As I said, we could add 2,400 temperatures if you got 3 hours to answer this question. You could plug X is 0.01 and 0.02 and 0.03 into our equation, get the Y value, write down 2,400 of those. And by the way, you could probably do that in Excel pretty quickly. And then divide by 2,400 and you have a really good estimate for average temperature. There's a part of me that wants to do that. I'm trying to decide, should I do that? Maybe we'll go back and do it. But again, doesn't this hint at what integrals do? Integrals add lots of little things together. Because think about what you're doing. Well, you're adding infinitely many things, but then you're dividing by infinity because there's going to be infinitely many of them. So you get a lot of temperatures, but then you're going to be dividing by 2,400. And you could say, no, I'm going to even more accurate. I'm going to go every 1,000th of an hour. And so I'll add all 24,000 of those temperatures, but then I'll be dividing by 24,000. So it's kind of like I'm getting infinity and divided by infinity. Well, here's the simple answer to this question. If I take the integral from 24 to 0 of our equation, which I'm just going to estimate, because notice the A value, you're not surprised that it's negative. I think I'll wimp out and call it negative 0.08 because there's a 0 after it. Does it make sense? That's a pretty good place to round. I'm trying to decide if I should include the 2 in it as well, but I don't want to. Negative 0.08 x squared. The B is 1.7716. I don't have a good reason, but I'm going to call it 1.772. And then the C is 30.3086. I think I'm going to call it 30.31. So I'm aware I'm getting an estimate for this, and that's fine. I want to know the average temperature. Do I really care to be accurate to the 100th place what the average temperature is?
Hey, Doug, I have a quick question for you.
Yep.
So when you were like kind of giving us some time to think, I tried to kind of go in Desmos and I did y equals and I did the integral with the A, B, and C. And then, so 2 questions, it didn't work. So I wanted to know why. And then second question was, do you add a constant at the end? Do you add D?
Yeah. Now, because we're doing what's called a definite integral, you don't have to add the D, or you can just say, well, I am going to add the D, but I'm going to make it 0 because it doesn't matter what it is. So you don't need to add the constant for a definite integral.
So as a definite integral, can you define that for me real quick?
It means those exist. There are limits of integration. You're
Okay.
going to get a numerical answer. In other words, you're looking for a particular area, you're not looking just for a formula that would find you all areas. If you're looking for a formula that would find you all areas, then you got to add plus D to your integral.
Okay. And so was the reason my formula didn't work in Desmos? Because I never added 24 into X, I guess. Is that the reason maybe? We have to
Yeah.
define that in Desmos?
That's right. And I think you can in Desmos. We'll go back and see if I can figure out how to get Desmos to cheat on this.
Cool.
But notice this is not a hard integral to take because again, this is in your wheelhouse. Like you can take the integral of squared equations. And so you say, okay, that's easy. I get negative 0.08 times x to the third divided by 3. And I could divide that and see what that is, but it seems like it's going to be a repeating decimal. And so I don't know, just leave it alone. And 1.772x divided by 2. 1.772 would divide by 2. Dividing by 2 does not produce repeating decimals. And so I'm tempted to do that one. And then 30.31 times x. And again, I'm very happy to find a 0 there, right? Because I don't have to put the 0 in. I just have to stick 24 into that mess. But my question to you is what am I going to get for this? I don't mean what's the number. I mean, what does this have to do with anything? Aren't I adding up? What am I doing again here? I want you to think about this. So I'm going to punch it all in, but I just want you to think, what does the answer to this mean? So negative 0.08 times 24 to the third, all divided by 3 plus 0.772 divided by 2 times 24 plus 30.31 times 24. If I didn't screw it up, which I think I did, I just looked and I didn't. Yeah, my 24 went in as a 4. It's a good thing I looked. I got 380. .06, so I'll just say 0.1. What is that? Is that degrees? Is it the sum of all the degrees? Like it's the area under the curve, but what does the area under the curve mean? Like what is that? What does that have to do with the temperature? It's 380 degrees outside. Like what? What is that? Think back to the units on this graph. What are the units? You should be able to tell me what that, if you can't tell me what that number means, you don't understand what you're doing just yet.
Isn't it the total amount of degrees you've gone in the day? If that makes sense.
You're going the right direction. What is this? What does the y-axis mean over here? What's the units for the y-axis?
Degrees.
Yeah, degrees Fahrenheit. What's the x-axis?
Hours.
Time.
Yeah, it's time, which in our case is measured in hours. What does an integral tell you about that red curve physically?
The rate of change.
You're thinking derivative when you say rate of change.
Tells you the area under the curve.
Tells you that area, right? So integrals tell you area under a curve.
Would it be the possible degrees that in any time given within that area?
It's pretty hard, isn't it?
So is it Fahrenheit over hours?
Yes. Remember the units. What are you really doing? You're adding a bunch of rectangles. Isn't the height of the rectangle Fahrenheit degrees and the width of the rectangle hours? There's your units. Fahrenheit hours. Which sort of feels meaningless, doesn't it? I have 380 degree hours. Huh? Degree hours? Degree hours. I mean, it's literally degree times hours. So the average temperature is measured in degrees, right? The question is, does it make sense to you then to get the average temperature that I would take 380 degree hours and divide by 24 hours? Because then the hours would cancel and I'd have degrees. So 380 really is kind of meaningless. because you're not getting the sum of just all of the degrees. You're not getting a billion. I would have thought if I added, the temperature at 1 and at 1.1 and 1.2 and 1.3, I'd end up with like a billion for my answer, because you're adding so many numbers. But we're getting the area under a curve, and the area under the curve has units. And in this case, the units are weird, degree hours. But if I divided by the range of hours, since I went from 0 to 24, that's going to give me my average temperature. What is 380? I'm going to stick the 0.1 back in there. 380.1 divided by 24. Uh-oh, I got 15.
I did that initially when you asked the question, and I got 15.83, which seemed really low.
Mm-hmm. Yeah, and I actually don't know why. I'm thinking right now, like, what? I thought the average was going to be like 33. I was about ready to condemn myself for being such a poor guesser, or to congratulate myself for being a genius. Something's wrong here. We should have got something like 33, shouldn't we, based on the graph? And the temperature never even made it to 15 degrees, so something's wrong here. Which, have you done enough math that you think, awesome, there's something to learn? My guess is, well, to me, there's one of two options. One of them is that we just made a math mistake. I made a math mistake and you guys didn't point it out because I'm the teacher, and you think, well, he knows what he's doing and I'm just learning. And so you thought I made a mistake, but you just felt like I don't want to say anything because I'm probably wrong. I understand that. Did anybody see any math mistakes that I made? Did I copy something down wrong? I typed a bunch of stuff in my calculator.
I just retyped it into my calculator and I got 869.136. And when I divide that by 24, I get 36.214.
So you're taking issue with the fact that the answer to this is not 380.1.
Yeah.
Again, this is cool.
I typed something wrong.
Well, your answer makes sense and mine doesn't, so something's wrong with mine. Let's see, I don't see anything wrong. Oh, I do see something wrong with one of my derivatives. I did something dumb. None of you even told me.
The x squared.
The x is squared. So, whoop. In my case, I'm going back up to that line where I typed all of this stuff. And I'm inserting a 24 squared. What I'm trying to show you how to do here, my friends, is how to fail. Like that. Again, I did not plan this. I often jokingly say I would plan these kind of things on purpose if I had to, but I don't have to. It just happens, and it happens to you too. Cool. There's something to figure out. In my case, I'm sort of happy to learn that my mistake was an accident, as opposed to I'm an idiot and I don't know calculus, since I'm the teacher and I'm supposed to know this stuff, right? So yeah, I got what Cheyenne got this time, which is 869. But one of the things I want you to notice is the only reason I caught my mistake is I took the trouble to look at the graph, and I'm always making sense of what I'm trying to do. The very fact that I stopped and said, I wonder what the average temperature is, and I took a guess at it, I was thinking, is the only reason I had a shot at figuring out what I did wrong. Otherwise, I'd have just wrote down 15 and, got an F on the test, so to speak. So let's see, does that make for a better answer? 869 divided by 24. Yeah, 36. 36.2 degrees approximately. So what did we just do? We didn't add 1,000,000 temperatures and divide by 1,000,000. We didn't add 1,000,000,000 temperatures and divide by 1,000,000,000. We added infinitely many temperatures and divided by, well, infinity. Keep in mind, in a sense, we're dividing by 24, but we're dividing by all the time slots that exist inside 24. So the kind of thing you would see in the book then, hence the average value of anything. And of course, when I say anything, I mean continuously. You already knew how to find the average before you got in this class, as long as the list was finite, as long as there was 10 items or 20 or 30 of them. What's your average test grade? Oh, no problem. I took 4 tests. I'll add all those up and divide by 4. But we're talking about things that change continuously, like temperature. But there's a lot of other things that change continuously. Like what about some kind of a blood marker, like you're sick, and so they're checking your blood for some certain chemical, and that's changing constantly. So the average value where things change constantly, and you have some reason to get it perfectly right, turns out to involve an integral. So what you're going to see, like for a formula in the book, would be something like this. If you work your way from B to A of any function times dx. Remember, that's just the y value or the height, and this is the x value or the width, right? So that just says add up a bunch of rectangles. So we're going to do what we've always done. Except for before we quit, we say divided by whatever that gap is. Divide by the range. And I just try to give you some sense of why that works. So my guess wasn't terrible. I was in the 30s, but I bet some of your guesses were better than mine. Do you think this is true? I'm actually just thinking out loud right now. So the right answer was actually 36, which is 32, 34, 36. Doesn't that seem high? That looks high to me. Why would that make sense? I thought my line looked a lot better. And I'm not kidding. Like, I actually think that. And I actually don't even know the answer to the question I'm asking right now. I'm just modeling how you do math. You think, you ask questions. Maybe you find the answers, maybe you don't. 36, that seems way too high. Like there's a lot more temperatures below that. Isn't it the place where there's as many temperatures above as there is below? I just find myself thinking that looks kind of high.
Perhaps it's because of your rounding.
Could be. Yeah. Remember that 0.08? That was my, if I didn't make a foolish mistake, which I ended up making, the important mistake would have been that A is so tiny, 0.08, that sometimes the 0.2 after that, or the 0.247 or something like that makes a difference. And had I carried those numbers out more completely, this answer might have changed more than I would have thought. And that really could be the answer. Maybe the right answer, if I didn't round so much, is actually a 35. Like it's pretty different. If you carry it out further, maybe it's still 36.3. And then I would say, oh, who cares? That's a good thing I rounded. If anybody does it. And remember, you can, if you're actually trying to answer this question, you don't do this algebraically. You cheat. You get your calculator out and just ask it to find the integral for you. So it's not that hard to get in your graphing calculator and type the whole thing in. While we're on that topic, let's go back to Desmos for a second. I'm pretty sure it will find the area under this curve for us. Remember, we just got done saying it was 860 or something like that. 869.13 based on what I did. I'm pretty sure you can do the integral in Desmos. I know I've done it before. It's just a question of whether I can remember it or not. I can't remember if it's listed in one of the functions or if you have to type it. Oh, there it is. I'm going to go do it over again just so you see it. I didn't know it was in there, so I'm all excited now. So over here in functions, there's 4 titles on the top. Trig, stats, distribution, I think. I'm not sure what that is. Is that? Yeah, distributions, it's statistics. And then miscellaneous, there's integral. Cool. Notice it does not allow me to do an indefinite integral. It wants a definite integral. So I can say, hey, 0 to 24. And if I was doing this in on my computer, I would be dragging the mouse over the top of ax squared plus bx plus c, which I don't think I can do here. I don't think I can do this with a pen, so I think I get to type it again. Go. Go. Like, how come it's not answering it? Notice there's a little triangle that says, basically, you suck. Why isn't it working? I'm actually glad this doesn't work. What's missing? There's something missing. What's missing?
The D over DX.
Yes.
The DX. I'm not sure why, but the programmers, maybe because they were math lovers, just wanted to force people into the, because we didn't really, remember what I said, we didn't really pay any attention to that, did we, a minute ago when we were doing this problem? But it doesn't like it. Now, I'm also not sure if I put DX here, do I need parentheses around AX squared plus BX plus C? My instinct is I don't, but notice it didn't work, so maybe I do.
The parentheses aren't helping.
Yep.
Oh, what the heck?
Let's see, I got 869 a minute ago, so that's not going to change that much if I divide 867. And by the way, is there any reason I couldn't just come back in here and say divided by 24? Apparently there is, because it didn't like that. Anybody think of a way I could do that? I thought that would work. Maybe out in front if I said 1 divided by 24. Ah, there we go. Didn't change that much, did it? So the rounding I did didn't make that much of a difference. So average value is kind of cool.
It's crazy that you don't even have to put it like in integral form, because I did it without the integral signs. I wonder if the DX would have changed it for me.
Right. And by the way, I think if you type the word, if you start typing the word integral, INT in Desmos, I think it goes, oh, and then it pops up that little S sign, which is what I usually do. It's just harder to type in this app that I'm using. I didn't even know that button existed over there until just now. Interesting. So you'll have a couple questions in your assignment that deal with average value. One thing that's interesting to me, for instance, I just got to kayak the Applegate River the other day, and it above Applegate Lake, it's just a super cool spot. But the river level was falling really quickly, like it had rained a bunch and ballooned way up to flood stage, and then it was dropping. Does it make sense when the river level's dropping? It's dropping like temperature did continuously. On the internet, I can see that the level was 1130, and then it was 1120, and it was 1110, but it was actually in the real world every single decimal between those. And so if I wanted to know what was the average level the river was at during the 1 hour I was on it, does it make sense I could use this and figure that out? Now I'd have to get the equation myself. What kind of an equation would I get? What kind of an equation models something that levels out like this? Again, I think if you speak the language of algebra, it'd be cool if you knew this. What kind of equations model something that levels out?
Is that e to the x? It's like, I know what equation you're talking about, but I can't quite remember.
Yeah, it's e to the x. You're right. It's e to the x. And a little more particularly e to the x, not entirely alone. A number in front of e to the x, like 5 e to the x, and then the x isn't alone. E to the 0.2x, for instance. So it might be like 7 times e to the 0.2x. So if I went into Desmos, I could say a times e to the bx power. That's what you were thinking of, Eve. And then it would actually find a pretty darn good equation that would model that. And then I could use this process and find the average level. And again, I would have to collect some data from the internet that would tell me the level at a few different time slots. And incidentally, on the internet, that level changes every 15 minutes. So I get an update every 15 minutes on the website that I look at. So that's just kind of cool to consider. So I just want you to think of things that change continuously. That's kind of the idea here. If you got that, you got all you need. One last thing, and then we can put this concept to rest. one last interesting idea. The mean is the technically precise way to say average, mean or average value theorem. If you go on in math, you'll hear the word theorem all the time, and it sounds real technical, but my own definition of that, which makes it partially true, I suppose, is I like to think of that as just like some truth in the universe. I should say some mathematical truth, because people don't give theorems for, like, if you jump off a roof, you're going to fall. That's not a theorem. Theorems are just math. So here's something that's true. Since the average we just discovered was really 36.2 rounded, which is the same answer we got, which is right about there. Does it make sense if the average is equal to 36.2, then the temperature had to be 36.2 at some point? This is sort of dumb. I like taking theorems or things people, teach in some sort of complicated way. I'd encourage you to go read this in the book. This is kind of a duh. If the average temperature is 36.2, then at some point in the day, the temperature was actually 36.2. Why would that have to be true, just based on common sense?
Because temperature is continuous.
Mm-hmm.
So it would have to hit that at some point.
Mm-hmm. And to be an average, wouldn't you have to have temperatures higher than that and temperatures lower than that? And because, as Alicia said, it's continuous, and that means if there was a low temperature of 15 and a high temperature of 80, and it had to climb continuously to 15 to 80, then it obviously had to hit that at some point. That's what the mean value theorem says. I wouldn't call that overly useful unless you go on in math. If you go on in math, that's a truth that gets used to prove some things later on. Is it possible to find it? Notice from the graph, I can tell it was about I got rid of the units. Is each box worth? Actually, you should be able to tell me that. Even though the units are gone, what's each box worth on the x-axis? Was it 1?
Looks like it.
Was it 1 hour?
It can't be 1 because this made it to 24, right?
Is it 2?
Must be 2 then, because that's only 12 boxes. So for that reason, this looks like about hour 4. And then in this case, there's even a second answer to it right out there. So 246, that was like hour 18. So degree, it actually hit it twice. Mean value theorem says there must be, mean value theorem will say something like this. There exists I want to say C, but we already use C, some constant, I'll say K. There exists a K such that Y of K is that average. That's the way a math teacher would say what I just said. What I said in English makes sense, but when you write it down mathematically, although it's really concise, sometimes it's hard to understand and it sounds confusing and you think, oh, math is hard. This is not hard. This is super simple. There exists some constant K, and I'll go up here and write K equals 4, K equals 18. And so you should say, yeah, that's not hard. Let's not do it, but what would you do if you needed to answer this? And why are you not surprised there's 2 of them in this case?
Because it's a quadratic equation, so you might end up using the quadratic formula and end up with plus or minus.
Yeah.
something square root over something.
Yeah, that's exactly right. Y of k being 36.2 is sort of code for y is 36.2. So you got to solve for x. Oh, it's a squared equation, quadratic form. There'd be two answers. Of course there would. So mean value just theorem says there exists at least one place where that happens. And in this case, algebraically, we could go get it. One other quick kind of example. I like to mountain bike. Mountain biking is quite simply riding your bike in the mountains. The other day I went for a ride. I wrote this down. And I went up and I rode at 4.4 miles per hour. But that's because I was climbing up the hill. When I went down, which is the whole reason I did it, I went 15.6 miles per hour. So I was working against gravity, went really slow. Gravity's helping me, going really fast. And you can also appreciate, I didn't go 4.4 exactly the entire time. It was just an average of 4.4 on the way up and an average of 15.6 on the way down. There were times when I was going 20 on straightaways and slowed down into corners and all those kinds of things. Is my average speed equal to 4.4 plus 15.6 divided by 2? Is that my average speed? Oh, I can do that in my head. That's 20. Divided by 2 is 10. Is that right? The answer is no. Why not?
You don't know how long you're going up and how long you're going down.
It does make a difference. This took 102 minutes for me to go up, but you can appreciate you were going a lot faster on the way down. It only took me 35 minutes on the way down. So the fact that I spent way more time at 4.4 than I spent at 15.6 would mean, take a guess. The average speed then would be more like what? What side of 10 is that going to be on?
The lower side.
Yeah. You spent, well, would you agree about triple the amount of time I spent going slow? So does it make sense that's going to drag your average down? The most useful thing I'm showing you today is not the mean value theorem, and it's not the symmetry thing. It's really finding an average of something. Well, look, again, I just want you to think about that in terms of an integral. If I went from if I spent 102 minutes going 4.4 miles an hour the whole time, minute 1, that's how fast I'm going. Minute 2, that's how fast I'm going all the way out there. And then I turn around and then suddenly I'm sort of flying 4 times faster. So I'll try to draw that roughly to average, but then I'm only doing it for a third as long. So that'd be 35 minutes added on to 102. So that gets me up to 137. So this is 35 minutes and that's 102 minutes. And that was 15.6. This is miles per hour on this part of the graph. Minutes over here. Most people have a pretty hard time if you said, okay, I threw that in there. Now what's my average? Well, you might visually or based on logic understand it's less than 10, but what are you actually going to do to come up with that? What would you actually do? Most people, even people that know as much math as it took you to make it into calculus, don't immediately know what to do. How do I get the 102 involved? how do I get the 35 involved? I mean, my temptation is to just, I don't know, throw them in there and like divide by stuff and multiply by stuff. And I can certainly tell that time is involved. It makes sense. You can't just ignore that. But my question is, do you see that in action here? What did this formula really say? It said find all the area and then ultimately multiply that by the range, right? Like how far did it go? It's literally kind of an area sort of a statement. Well, in that parabola, we had to sort of use calculus to find the area, our knowledge of an integral, but isn't an area down here a little easier to find? Like I don't need to make an equation for this. Isn't this 102 times 4.4? Isn't that the area of that? If the height is 4.4 and the width is 102, it's a rectangle. I don't need calculus to find the area of a rectangle. If you like pain, you can make an equation out of that horizontal line. It'd be y equals 4.4. Take the integral of 4.4. It'd be 4.4x. It actually still works. And isn't this area up here 15.6 times 35? And so I find those two areas.
So are you basically adding your speeds 137 times?
Yeah, kind of. What you're really doing, and again, think about units here because the time isn't the same. One time is hours and one time is minutes. And I could have changed that if I wanted to. And had I done this, it would have looked a little nicer. Because remember, miles per hour is miles over hours. And had I made this hours down here, then I would have multiplied miles per hour times hours. And so when I multiply 102 times 4.4, the answer would be a length. Does that make sense? It's like miles. I'm sort of tempted to do that. I don't think I will. So in this case, because I'm multiplying, I'm really getting mile minutes per hour, if you will. So 102 times 4.4 is 448.8. And the units of that would be miles per hour times minutes, which I think I'll write as miles per hour times minutes, or mile minutes per hour. Again, does it make sense? It would have looked so much nicer if I changed that 102 minutes into whatever that is, 0.8 hours or something, because then the hours would have canceled. The point is, this unit here is really miles. It's a distance. That's a distance. This unit over here, kind of the same thing. It's also a distance. When I multiply that, I got 546. So it's a distance. So if I come back and I add those two together to get the area, so now I have the area under the curve, but then I divide by the fact that this whole distance all the way over here is 137. I'm dividing miles by minutes, in a sense, or I'm dividing my area, which is miles, divided by my time, which if I had changed it into hours, it'd be miles per hour. Do you see the logic in why you're doing that? Why that formula works? Why this cool?
It's miles minute per hour, right? So you're going to be left with miles per hour.
Yeah. So I made this look a little bit worse, but in the end, then what I'm taking is 546 plus 448.8, which is really 994.
I got 409.6.
For what? Did I get something wrong?
102.4 times 4.
It's 102 times 4.4.
Oh,
That is
just
very
kidding.
clearly. So then if I divide by 137 minutes, even though I didn't change it, does it make sense the minutes cancel and now my units are back to miles per hour? Again, I'm just showing you the logic of this. And so in the end, that's how you get your average here. Now this wasn't, in this case, my speed wasn't changing constantly. Remember before, our temperature changed constantly, but you're still doing the same thing to find the average. And so when I do that divided by 137, I actually get a speed that's a little bit more reasonable, about 7.3. So my average speed was really 7.3. And that's pretty interesting in this case to know what your average speed was. And it was very much skewed by the fact that I spent more time slow than I spent fast. And this factors that in. And it's just showing you the logic of why our average value formula says, we'll change colors, says find the area and then divide it by the range or the domain. Why that works. I just didn't have to use calculus to find the area this time. That's the only thing that changed. Cool. Okay, so we are done with 5.3 and 5.4 this week. So you are tackling those two in your MyOpenMath. I hope you're not saving that take-home quiz I gave you till later. None of you are starting class saying, hey, I got stuck on number 17. Can you give us some help? So be working on that quiz. We're getting close to that quiz being due. I think it was due the 25th, which is Monday. So you're going to owe it to me Monday. I didn't say what time Monday, which sort of means Monday night. So if I get it Monday night, I'll basically have Tuesday to get it graded. And then I can give it back to you Wednesday when we're reviewing. You'll have it back to you by Wednesday when we're reviewing for the test next week. So you should be asking me questions about that perhaps, because Monday will be the last day you can ask me questions about it since it's due that night. So ideally you come to class next week with all of 5.3 and 5.4 homework done and the quiz done, or at least down to where there's one thing you don't understand. All right, I need to shut up, get y'all out of here. You guys have a great weekend if I don't see you before then.
I just wanted to ask real quick on problem. So on the take home quiz, there's like problem 2, 3, and 4 that are Excel based. And I just want to make sure I'm doing them right. So if I give you the answer to one of them, I mean, if I tell you what I got for my answer for one of them, can you tell me if I got it right or not? Just so I know if I'm doing it right.
Absolutely. Which one?
So I'll just do problem 2 because it's the first one. For number A, did you get 41.59803?
Yep.
All right, cool.
You are.
Thank
doing
you.
it right.
Have a great weekend.
And I didn't tell you how to round on that too. So as long as you chose something reasonable, I rounded a little closer than you did, but good job. Yep. Have a good weekend. Keep going if you have other questions.
I have a question from back on the notes. I tried plugging it in and I don't know if it's because of how I'm plugging it into my calculator.
Mm-hmm.
It was the negative 0.08 x to the third over 3.
Yeah.
I would be plugging in 24 as my x, right?
Mm-hmm.
And so when I would do that, I would get like a really like significantly smaller number than 869, I think.
That was the answer I got for all three of them added together with 24 plugged into everything, not just the 0.08.
Yeah, so let me see if I can go back in my calculator.
So
yeah, I was getting like I got like 3 different answers. So there's definitely something wrong with how I'm plugging it in.
Just tell me out loud what you plug in.
Okay, so I did, I first did 24 to the third power.
Okay.
And I multiplied that by negative 0.08.
Mm-hmm.
And then I divide that by 3.
And you did say because it's when you say times negative 0.08, you actually have a multiplication sign. Otherwise, it thinks you mean minus 0.08.
Yeah. Mm-hmm.
Okay.
And so I got negative 368 for that part.
Okay.
Is that what you got at that point?
I'm going back to, oh crap, I think it just went away. No, it didn't. Yes, it did. Yep, negative 368. Yep.
And so then I do 24 to the second power,
Mm-hmm.
and then I multiply that by 1.772, and then I divide by 2,
Yep.
and then I just add the 30.31 onto there.
That's also multiplied by 24 though.
There we go.
Because
That's
it grows an X.
Yeah. Okay, I got it now. Thank you.
Good. I'm glad somebody besides me made a dumb mistake today.
I just had a question, and if we want to like double check our answers, is the best way to contact you like through email or like the MyOpenMath message thing?
Either one, it doesn't make any difference. I'm usually checking both of them. When you do it through MyOpenMath, I get if I'm not in my email, I get this little pop-up on my screen that tells me something just came in, which is sort of helpful. Whereas email, I kind of go check it occasionally.
Okay.
So yeah, feel free to send me, say, hey, I got this for question 7. Is it right? Great.
Okay.
Great idea.
Thank you.
Yeah.
See you Monday.
I had a question, although I'm not sure if this is something you can help with. At the beginning of class, we were putting in that function, I think it was y equals x squared minus 2x plus 4.
Into the graphing calculator?
Yeah, I tried putting that into my graphing calculator, and it was giving me invalid dim error.
That's for the one that I have up right now, the x squared minus
Yeah.
2x plus 4. So you just
Yeah.
type in that in your graphing calculator?
Yeah, I did y equals, well, the y equals button and then x squared minus 2x plus 4.
Let me show you something. Usually when you get that error, it's because you graph something and you control the window of the screen and you do something that doesn't make sense. So I'll show you what I mean. So for instance, here's this graph right here. And if I go to window, see how it says X minimum is -10 and X max is 10. If I put X minimum is 3 and X max is -2, does it make sense that's backwards? You can't have a minimum be 3 and then a maximum be smaller than 3. So if I say graph, no, that's not the what you got. So you couldn't get it to graph, or you couldn't get it to tell you the answer to the integral.
I couldn't get it to graph. Like, I put in the equation and then I hit graph and it would give me that error. So I can
try this just right now. Like every time I graph, because the window might be screwed up, I always hit zoom and then 6 for zoom standard. It like fixes the window. Try that really quick.
Okay. Yeah, I hit it showed the window real quick and then it immediately changed to that invalid dim.
Oh, okay. I know what it is. I know what it is. If you go into stat. See how see a stat right here?
Yeah.
Hit stat. And then go to edit. What do you see?
Nothing.
Nothing.
Yeah. I had edited this yesterday because I was doing some physics homework, so I did have data in there. But once I saw that error, I thought maybe I should clear out my stat list. So that's empty.
When you go to this screen, look at my screen. When you go to this screen, that is the problem. I'm not wrong about that. But if you go up here and I hit enter, Is that highlighted for you like it is for me now?
Yeah, it's highlighted.
That's the problem, because you're telling it to graph points and then it goes into the white, into the stat screen and there's no points to graph. So it's saying, dude, you're asking me to graph and there's nothing to graph.
Okay, so deselect that.
Yeah, just go up and highlight it and hit enter, and it'll graph now.
Yeah, it just graphed it. Okay. Thank you.
Good question.
And are you going to be in your office hour later today?
Yeah,
Okay. Because I'm going to start on the online homework and I will probably show up with any questions I have about that.
okay.
So I'll talk to you later. And if not, have a good weekend.
Okay, sounds good, Cheyenne.